In this lesson, we shall focus on applied mathematics, numerical methods too, and we shall be looking at a wide range of topics. But to start with, focusing on past assessment questions, past examination questions, is the following notion. Right, I want us today to start by looking at this notion that remains at the heart of this module and a method that we need to learn. The second order Runge-Kutta method. Right, it is very much examinable and we need to spend some time to learn this method. But to learn this method very effectively, there's something we call the second order. Right, it is called the second order. Second order Runge-Kutta method. Second order Runge-Kutta method. With yn plus 1, which is yn plus 2 over 3 k1 plus 1 over 3 k2. This becomes what we call the Runge-Kutta second order Runge-Kutta method. The k1 is actually equal to h f of xn yn. K2 is hf tn plus 2 over 3 h yn plus 3 over 2 k1. Right, so we have exactly this method here. We have exactly this method here. So now, this is the second order Runge-Kutta method that we actually obviously use. And here comes the question. The question says, consider a system of what we call coupled second order differential equations. And these are referred to as coupled second order differential equations because of the fact that you have two differential equations which are second order differential equations. But these second order differential equations have been given obviously here with some initial conditions. With initial conditions, u at 0 is 1, u primed at 0 is 2. For instance, v at 0 is 3, and also what we call v primed at 0 becomes a 4. Becomes exactly a 4 there. So now the second order Runge-Kutta method with h equals 0.2, a equals 2/3, b equals 1/3, and alpha equals beta equals 3/2. 3/2. Therefore, we actually need to use this second order Runge-Kutta method. What are we supposed to do? We need to find u primed, v, and v primed at t equals 0.2. At t equals 0.2. At t equals 0.2. Right, so we continue. We continue to solve this particular problem. Let's start with our solution for this one. To start, we begin as follows. We look at the fact that what we have here is that we've been actually given what? So the solution begins as follows. So we have been given, right, we have been given the following. Right, we've been given We've been given u double primed minus 2 plus 1 u primed squared plus 2uv minus u cubed equals cosine t. So, which is 2, this second one, 2v double primed plus the trigonometric sine of t, u primed v primed minus 6u equals twice t plus 3. Okay. This is the case with u0, 1, u primed of 0 equals 2, v of 0 equals 3, v primed of 0 equals 4. Right. So this is what has been given to us. Okay, now, given as it is, we've seen the Runge-Kutta method of second order. So first things first, right? What we do is we actually attempt to convert. So we convert the system that is given, the system of two differential equations, the coupled system. Right, we first convert the system of second order differential equations to a system of first order. First order differential equations. By doing what? How do we perform that? By introducing, two new variables. Right, by introducing two new variables which equal the derivatives of the original variables. Okay. First, we convert the system of differential second order, the system of second order, differential equations to a system of first order differential equations by introducing two new variables which equal the derivatives of the original variables. To convert the second order differential equations to first order differential equations. So this conversion is very important so that we're able to solve this. Why do we need to convert? Because when we perform the conversion, this is actually consistent with the fact that we actually be in a position to use exactly this particular method to solve the problem at our disposal. So we convert the second order to the first order differential equations. Let us go through these step by step and try to make sense of this. So to convert this problem for it to work, we begin as follows. Okay, so this is the sort of popular question you can expect to meet. We call U primed, we call it W, and V primed, we call it X. And if we actually are able to do this, then the original differential equations can be written as W primed T plus 1 W squared 2UV U cubed plus cosine T. Right, and simultaneously we have also X primed, which is 3U minus 1/2 the sine of T. We shall discuss this just now. WX T plus 3/2. And this arises from division in the second equation. Now, U primed is W, so that in the place of this one, we have W, but the fact that we have U double primed, it means the following, right? So you have U double primed, but U double primed is U primed primed. So that in the place of U primed, you put W, and therefore it becomes W primed. Is therefore equal to T plus 1. The U primed, you call it W. So it's going to be W squared. And then obviously you have the 2UV. And then if you move everything across, the negative U cubed becomes positive. And then obviously everything is added to cosine T on the right-hand side. You divide through by 2. And then now you have V double primed, which can be converted, because if you look at V double primed, it is the same as V primed. So we have the first derivative of V, and you're taking again another derivative. Okay. And so we are able to see this. We are able to notice this. And so at this point, it means that V primed is X. So wherever V primed is X, there's going to be the following, right? So it means that V double primed is X primed. So you can put actually X primed there, and then it is actually equal to this one here. It becomes so exactly equal to what? So this 6U you divide by 2, it becomes a 3U, but you move it across, becoming positive. Minus 1/2 the sine. U primed, V primed, they are like WX. And then here you have the 2T, and then you have the 3/2 as well, because we have divided by these 2 there, both sides of the equation. Okay, what is the aim of all these things we're doing? We are given second order differential equations. We've managed to convert them to first order. Okay, let us continue now with our analysis of the formulas we've written to solve this particular problem using the second order Runge-Kutta method. By dint of these, we then say therefore the corresponding system, right, of first order System of first order differential equations. Right, differential equations is, so therefore the corresponding system of first order differential equations is the following. So yeah, the system becomes, we called U primed, we called it W. V primed, we called it X. We got another equation that became W primed, which became T plus 1. W squared minus 2 UV U cubed cosine T X primed is 3U minus 1/2 the sine of T WX T plus 3/2. Which means, therefore, you have U at 0 is 1, V at 0 is 3, W at 0 becomes 2. I'm going to check this one and make sense of this particular system right now that were formed. Let us reason together. Okay, we decided that to remove the U double prime to the V double prime and convert the second order to first order, we said let U prime to be W, V prime to be X, and therefore this was converted to this. So now U at 0 is 1, V at 0 is 3, but U primed is W. So that here we can say W, this one U primed at 0 is 2, we can call it W at 0 is 2. In the same way, that for instance, obviously we have V at 0 is 3, but also there is V primed. V primed at 0 is 4, it means therefore X at 0 is 4. X at 0 is 4. X at 0 is 4. Right. X at 0 is 4. X at 0 becomes 4. Okay, now let's have that and think about this. This is the new system. So we're given second order differential equations, but we converted them right now to first order. Right, and so that is what we're able to see. The question is, what do we then do at this point moving forward? We shall be able to continue and solve this particular problem step by step as follows. We note that a system, right, so a system of first order ordinary differential equations such as 1 can be solved by any of the methods, right, in a given chapter. So at this point, it can be solved by any of the methods in chapter 6 I'll mention that in detail, and obviously there is also chapter 5 in the prescribed book. All right, also in chapter 5 of Gerald. Although obviously we agree that the algorithms will become very complicated if the system is large and one of the higher order method, right? One of the higher order method or methods is used. Okay, so it is a comment that a system of first order, because now we have a system of first order. We converted the second order to first order. We are dealing right now with a system of first order differential equations. And we're then saying a system of first order ordinary differential equations such as the one we've just written now, can be solved by any of the methods in chapter 6, chapter 5 of Gerald. Gerald is a prescribed book. We call it Gerald because the author is Gerald. So now, although the algorithms will become very complicated if the system is large, and one of the higher order methods is used. So we resort to the higher order methods sometimes if the system becomes so much complicated in the process. So we resort to the higher order methods that are part of this module. Let us continue with our analysis of this particular problem step by step. Let's continue with our analysis of this particular problem step by step. There are a couple of things that remain at the heart of operations for this particular problem here. So in other words, now to see how the algorithms can be adapted to systems such as one, note first that the system one can be written as. So to see how the algorithms can be actually adapted to systems such as one. We want to adapt these algorithms to the system such as one, the one we've just written of first order. Note first that the system one can be written as. Right, let us write the system one as our U primed. We can write the U primed as big U. Then we write T, U, V, W, X. V primed. It's V, T, U, V, W, X. W T U V W X primed. We're going to call X primed big X T U V W X. Then we're going to call small u at 0. Right, small u at 0 remains 1 still. Big V at 0 remains 3 from the problem. W at 0, that is what we actually have. It is 2 because we know that W is equal to U primed. So X at 0 is 4 because we know that V primed is equal to X. And so now we have this and we're going to write them down like this. So we actually, from the first order equations we've written, we'll be able to write this out. Okay, these questions normally repeat. So the tendency in the second order, you'll see that in this module, we deal with mostly the second order differential equations than like higher order. So the second order, it's the highest we deal with. So if there's anything that can change here, would be the right hand side. They can just change and put sine t here, but the method, the modus operandi will be the same. In which case, now let us continue with our analysis of these and make sure that we are able to understand exactly what needs to happen here. So then we'll have the following. We'll then have the following. Okay. This is the case where you have U, T U V W X, and it is U primed, but U primed is the big U, but we know that U primed is W, so we're gonna make this one W. It is U primed, but also this big V is V primed, but V primed is what? It's small x. So we're going to write TU V WX, which equals X. Now W, big W is equal to W primed. Big W is W primed. But W primed, if W is U primed, it means that W primed is going to be U double primed. And U double primed is going to be exactly this, but you move everything to the other side. So in other words, we're going to have big W of TU VWX, which is T plus 1 W squared minus 2UV plus U cubed plus cosine T. And then we're going to have big X of TU VWX. Okay? So we remember something, that big X is X primed. But if X is V primed, X primed is V double primed. But V double primed is going to be these things now. You move and divide by 2. So like that's minus 6u divided by 2 is going to be minus 3u, but you move it across, it becomes exactly 3u, and then it's going to be this one divided by 2, this 2, divided by this 2, dividing by 2, dividing by 2t by 2, it becomes t, and then this is 3 over 2. With that, we're able to then see that this is going to be exactly 3u from this second equation, minus half, you divide by 2 here, and then move the sign to the other side, making it sine t. Wx plus t plus 3 over 2. Okay, so we can therefore be in a position to write the equation like this: UVWX. Right. And we reiterate one fact that we used in the study of the Euler method. And we said, therefore, and we reiterate the fact that actually in this case, the basic idea, right, the basic idea is to adapt. Is to adapt the algorithm the algorithm for solving problems of the form y primed equals f of ty, such that the initial value is y of t0 becomes exactly y0. Is to adopt the algorithm for solving problems of the form, right, to solving problems, right, problems of the form right of the form. Now we're going to call this form, we're going to call this form 2. We're going to call this form 2. And then, whereas now, because we're going to be using these numbers from time to time, so you have this one here. This is the form 1. This is the form 1. Right, it is exactly the form 1. The basic idea is to adapt the algorithm for solving problems of the form y primed equals f of ty, where y of t0 is y0, to solving problems, right, to solving problems of the form 2, the form 2 that we've just written now. Okay, obviously the form 2 by replacing, right, by replacing y by u, v, w, and x, and replacing f by u, v, w, and x. Moreover, note that the algorithm is not carried, right? It's not carried out separately. It's not carried out separately. For each unknown, right? For each unknown, but it's not carried separately for each unknown, but simultaneously, right? But simultaneously. Okay, we're discussing the second order Runge-Kutta. That is why we're discussing this. For all four. Right, for all four. So in other words, the basic idea is to adopt the algorithm we're looking at for solving problems of the form y prime because f of t and y, and also y at t0 is y0. To solving problems of the form 2 by replacing y by u, v, w, and x. And u, v, w, and x, they give us like 1, 2, 3, 4 variables to deal with. I'm replacing f by u, v, w, and x. Note that the algorithm is not carried out separately for each unknown, but simultaneously for all. But simultaneously for all. But simultaneously for all. Simultaneously for all. For all four. Because you have 1, 2, 3, 4. Let's continue with our analysis of this particular problem. In this case, what do we do? In this case, right, in this case of the second order, right, of the second order, Runge-Kutta. Second order Runge-Kutta method with A equals 2/3, B equals 1/3, alpha equals beta equals, so yeah, we are using these things here. A equals 2/3, B equals 1/3, alpha equals beta equals 3/2. The algorithm. Right, so the algorithm for 3. Okay, so we're going to call this one 3. Right, we're going to call this one equation 3. We're going to call this one equation 3. Because the basic idea is to adapt the algorithm for solving problems of the form. So we wish to adapt it and use the algorithm we use to solve equations of the form this. Okay, so let's continue and take a look at what is happening here. Okay, for 3 is, so now we're going to have yn plus 1. Yn 2/3 k1 plus 1/3 k2. There's also k1, which equals hf of tn y sub n. K2 equals hf tn plus 3/2 h yn plus 3 over 2 k1. In this case of the second order Runge-Kutta method with these, the algorithm for 3 is this one here. It is this one here. Okay. So the algorithm for 3. So in other words, when we want to solve an equation like this, y prime equals f of t and y, and also y at t0 is y0. We want to solve this equation. What is the algorithm to solve this equation? The algorithm to solve this equation is this one. So the algorithm for 3 is y sub n plus 1 equals y sub n plus 2/3 k1 plus 1/3 k sub 2. K sub 1 equals h of f t sub n and y sub n. K2 is hf of t sub n plus 3 over 2h y sub n plus 3 over 2 k 1 or sub 1, subscript 1, that is. Okay, now we continue to then say, given these, we can proceed to do the following. So we can then say, adapted to the system 2. Right. So this one here, and we continue to then say, adapted to the system. To the system 2. This gives us the algorithm which is the un plus 1, un 2 out of 3 k1, or we're going to write, adapting it, we're going to use 2/3 k, but we're going to call this ku1 plus 1/3 of ku2, but we're also going to have vn1, sub n plus 1 is vn plus 2/3 of kv1 plus 1/3 kv2, which is this one, is wn plus 2 out of 3 kw1 1/3 kw2, which is xn plus 1. It's xn plus 2 over 3 kx1 1 over 3 kx2. Right? Remember UVWX. So we can be able to write these equations like this. Now we're writing this equation because they're saying adapted to the system 2. So we have this here where the yn plus 1 can be written like this, but the system 2 is this one here. It is exactly this system here. So we adapted to this system. So this system has UVWX. That is why then we say for the U, then it's going to be U1. For the V, it's going to be V1, W1, X1 as well. Okay, we're going to understand this method better. Now let us continue with Runge-Kutta second order. Runge-Kutta second order. So now we're going to continue to then say the K subscript U1 is HU. H big U. And this is TN, UN, VN, WN, XN. KV1, HV. Okay, this one is big U. So there's big V, which is, so the KU1, we mean this one. The KV1, we mean this TN, UN, VN, WN, XN. And then there is KW1 because U, V, W, X, those are the variables. So this is actually a W, and it is having the same arguments. So TN, UN, VN, WN, XN. Then we have KX1, which is HX, TN, UN, VN, WN, and XN. So because there are these things like U1, so we have KU1, KU2. Right, so KU1, KV1, KW1, and then also there is KX1. So those are these here. X1, and those are the KX1, and the KU1, the KV1, the KW1. Now, there are the next things. KU2, which means HU, which is TN plus. So we're dealing with the KU1 up to X1. Then now we're dealing with KU2, V2, and so on. So KU2 is going to be TN 3/2 H, UN plus 3/2. So now the KU2 is written in terms of the KV1 and also VN plus 3/2 KV1. And then also WN plus 3/2 KW1. XN plus 3/2 KX1. And then you have KV2, which is HV, which is TN plus 3/2 H, UN plus 3/2 KV1 plus 3/2 KV1. Okay, a lot of the adaptations here. VN plus 3/2 KV1. WN plus 3/2 KW1. XN plus 3/2 KX1. Like so. And then now we also have KW2, and then we're going to have KX2. Okay, because we had KU1, V1, W1, X1, and then now there's KU2, W2, V2, W2, and X2. So the KW2 is going to be H big W is TN plus 3/2 H UN plus 3 over 2 K V1 Vn plus 3 over 2 K V1 Wn plus 3 over 2 KW1. Okay, so this is like Wn. Okay, and then we have the last one, Xn plus 3 over 2 KX1. And then we're going to have also the KX2. H big X. Tn plus 3 over 2 H. Un plus 3 over 2 KV1. Vn plus 3 over 2 KV1. Wn plus 3 over 2 KW1. Xn plus 3 over 2 KX1. Okay. Now we started off with this. We started off with the KU1, KV1, KW1, and KX1. Right. Okay, we continue. Right, so then you have KU1, KV1, KW1, KX1. KU2, KV2, KW2, KX2. Hence, right. Okay, we continue, please. Right. Okay. Now, I want us to look at the fact that we have the case here. The KU2, KV2, KW2, KX2. And then there are other things that we're going to do here. So we'll then continue to then say, hence with H being 0.2, we calculate U at 0.2. V at 0.2. U primed at 0.2. V primed at 0.2. From the given initial values as follows. Okay. I want us to look at the following. So you'd have to remember that the KU1 is H big U, Tn, Un, Vn, Wn, Xn. KV1, HV, Tn, Un, Vn, Wn, Xn. KW1, H big W, T sub N, U subscript N, V subscript N, W subscript N, and then Xn. KX1, H big X, T sub N, U sub N, V sub N, W sub N, X sub N. So now, if we're dealing with the following, right? If we're dealing with the following, right? So, okay, we're continuing. Right. Okay, we continue. Right. Right. Okay. Yeah. Okay. My dear. Yeah. I'm gonna actually give you a call after 12. After 12. Okay. Thanks, my dear. Okay. We continue. So now we're gonna have the following. Right. Right. Okay. We're continuing, please. Okay. Okay. Now let us actually look at this case. Says, and if we're then saying, hence with H equals 0.2, H is 0.2 in this problem. And also, we have, okay, we calculate U at 0.2, V at 0.2, and also U prime at 0.2, V prime at 0.2. Okay. And if we do that, this is actually going to mean the following. It's going to mean exactly the following. That this KU1 is actually exactly the same as 0.2, because H is 0.2, but it's going to be big U. This H.2 is going to be sort of evaluated at KU1. Right. So at evaluated KU1, it means that you're going to have 0, 1, 3, 2, 4. Let's discuss this. So obviously at this point, if we are to deal with H equals 0.2 and we're dealing with KU1, you would have therefore the following values. That in the beginning, what we actually have here becomes that you would have the T in the beginning. What would the T be in the beginning? 0, 0, 0, 0, 0. And then there's a U at 0. It is 1. V at 0, 3. W is like U prime at 0, which is 2. Xn is like v prime at 0, which is v prime at 0, which is 4. That's why we have the 4 here. But now this big U is has its origins here. Has its origins right here, this big U. I want to go back to where we set the scene. This big U is equal to W. But W is the same as what? Is U primed. So, but U primed is equal to what? U primed at 0 is equal to 2. So we're going to come here. We're going to come here and then say the following. So this is still 0.2. And then this U is W, but W is U primed. U primed is what? Is only 2. If you multiply 0.2 by 2, you get 0.4. Now there's KV1. It's 0.2. And the V, etc., etc. This V in the beginning at 0, T0. In the beginning, 0, 0, 0, 0. So it's going to be 0. And then now there's going to be U0. Right. So what is U0? It's 1. You have a 1. So the rest of these things are the same. Like 3, 2, then 4. Which is 0.2. 0.2. And then now you have the V. But we remember something here. What is big V? What is the big V according to what we said? We come back here and say the big V is X. But this X is V primed. Big V is X. But X is equal to V primed. And then V primed at 0 is what? It's a 4. It is a 4. So you're going to come here. You're going to come here, okay, and put a 4 there. Okay, this question does not change very much, please. So the way we are doing it here is how you need to deal with the second order Runge-Kutta method. Second order Runge-Kutta method. Second order Runge-Kutta method. So we continue. We continue. Okay, let us look at the next one. So the next one is H big W. Okay, but obviously H you already know in this problem is 0.2. So you're going to put 0.2. But what is big W? Okay, so we set the scene. So big W. Big W. So big W is equal to what? It's equal to all these. It's equal to all these. So, but now where can we see it? The big W is like this one here, and then everything has been moved to the other side. And then you're going to have the cosine T, and then you have a T plus 1, where we agree that W is U primed. So in the place of U primed, we put a W. So it's going to be W squared, and so on and so forth. So W is the first equation. And the same as in the same way that the big X is this second equation, but the other terms transpose it to the right-hand side of the equation. And so now we are able to say, okay, let us deal with W. So now, yeah, You see, the same way that we got the other things like the UV, the W is not different. So, which is 0, 1, 3, 2, 4, which is 0.2, which is 0 plus 1. Okay, because now at this point, it means that this one is going to be our T. It's going to be our T, our U, our V, our W, our X. We put them here. But our T then is going to be, our T is 0. So it's going to be 0 plus 1. And then this one is going to be our W, because W is U primed. So, but what is W here? W is the second last. Use that, and that becomes 2. So that would be 2 squared. Here, 2 squared. Plus 2 times U. U is this one. And the second one is a 1. Okay, but it's negative because we're moving it to the other side. Everything is moved to the other side. So, like we saw before, so it means therefore, I mean, what we're saying is that U double primed is, if you move this thing to the other side, it's going to be T plus 1. So the signs will be like complete opposites. And then that minus 2UV plus U cubed plus cosine T. Plus cosine T. So minus 2 times 1. Okay, so U is 1. V is 1, 2, 3. 1, 2, 3. So the V is 3. Like this. And then it's going to be a plus U cubed. U is the second one. Second coordinate, the second one, so it's going to be 1 cubed. Cosine T. So it's going to be like cosine 0. Okay, if you do everything, then you get a 0 here. Because this one is 2 squared. It's a 4. Minus 6 is minus 2. Minus 2 plus 2 is 0. So now, we continue. Sorry, we continue now. And then we're dealing with the KX1. Okay, the H remains 0.2. And then it's big X. Okay, it's going to be BX, same thing. 0, 1, 3, 2, then 4. Okay, now, okay, then you have 4 here. And then you have 0.2. Okay, because it's 0.2 outside, everything is like this. So this is how we solve the second order. Obviously, Runge-Kutta. And then now when I have the big X, the big X is going to come out of these. So out of that, the big X is going to be, for instance, you're going to have the V double prime equals, okay, divide by 2. So it's going to be like minus 1/2 minus 1/2 the sine of T. U primed V primed plus 3U T plus 3/2. So now you have 3. What exactly is the U? U is the second component. The second component is 1. Then now, okay. Then you also have the minus 1/2. You can write it as minus 0.5, 0.5. And then now, u primed. What is u primed at 0? Right, so you'd have u primed. And u primed is w. And w becomes what? W, for instance, is going to become exactly a 2. So let us deal with this. So it's minus 0.5. And then, okay, it's going to be the sine of 0. Minus 0.5, the sine of 0. U primed is w. U primed is w. But w is the second last component, second last, giving us a 2. And then now there's also v primed. But we remember v primed is our x. V primed becomes our x. So if v primed becomes our x, what do we get? Yeah, our x is the last one. And the last one becomes exactly 4. Okay. Now, so now you have the following. Yep. Okay. We're still looking at this one. And then there's a, okay, we dealt with the 3u there. And then now there's t. T. The first one is 0, like t0 is 0. And then you also have there, which one? Okay, the 3/2, this 3/2, you can write it as 1.5. And then we use a calculator to do everything here. But this one becomes a 0.9. You can just verify quickly. Okay, because 0.2 times 4 is 0.8 is obvious. Because we know 4 times 2 is 8 in the decimal. Okay, but now I'm interested in us just confirming. Okay, confirming 0.2. 3/1 minus 0.5 by the sine of 0, close bracket, times 2 times 4 plus 1.5, which is 9 out of 10, and 9 out of 10 is 0.9. So that gives us actually the answer there for the kx1. So we got all the values, ku1, kv1, kw1, kx1. Okay. And then after we got these ones, we need to get also the subsequent ones. So we need to get the ku2. Hey, okay, it's a marathon this. So now we remember that we have the ku2, kv2, kw2, kx2. What is the use of these things here? Okay, the use of these things here is in the calculations, because we know that we want to solve adapted to the system. This gives us the algorithm. This is the algorithm. In this algorithm, we're going to have ku1, ku2. So we got ku1, kv1, kw1, kx1. Then now we're going to do ku2, kv2, kw2, kx2. And then we come and substitute everything here, and then we shall get the answer. But now we've just got the ku1, kv1, kw1, kx1 the way we've done it. And then now we're going to get the next one. We're going to get the next thing. So in the next case, we're going to get the ku2, which is this. This is the formula. So ku2 is this, kv2 is this, kw2 is this, and kx2 is exactly that one. Let us continue with our analysis of these. So to analyze these, we're going to do the following. we're going to do exactly the following. Right, we're going to do precisely the following. We're going to do precisely the following. Let's continue now with our search for the solution. So, right, looking at our search for the solution, there are a couple of things we need to take into account when we discuss this. It is the fact that, for instance, let us first analyze our KU2. Right, so KU2 is equal to, this is the formula. We've written the formulas, but we write big U, Tn plus 3 over 2H, Un plus 3 over 2 KV1, Vn plus 3 over 2 KV1, Un plus 3 over 2 KW1, Xn 3 over 2 KX1. So now, okay, we're going to do KU2. So KU2 is H. This H is 0.2 U. And then there's T0. T0 we saw it's 0. And then there's 3 over 2. H is 0.2. We saw it here. And then now we're going to have the U0. U0 is 1. And then there is 3 over 2. KV1. We did KV1, but we got 0.4. And then there is V0. V0 is exactly 3. Then we have 3 out of 2 here. But we did together KV1. And in the case of KV1, we got 0.8. And then we actually, therefore, dealt with W0. But U primed is W. U primed is W. So this one is going to be exactly a 2. 3 over 2. KW1, we got it together, which became 0. And then X0. X0, remember that X became V primed. So which means X0 is V0 primed. And V primed of 0 is a 4. And then we have 3 over 2, and then we just got KX1. We got it to be 0.9 just now using a calculator. Okay, let us deal with this. KU2 is 0.2, 0.3, 1.6, 4.2, 2.0, 5.35. Okay, you can just check some of these. But 4 plus 1.5 times 0.9. Okay, testing if these things are numerically correct. So you're going to have, for example, 4 plus 1.5 times 0.9. Let's see what you're getting. Okay. We're getting 5.35. So in the same way, the others will be obtained. However, let us continue with our analysis of these, which is actually 0.2 times. So if you're dealing with a big U, but we remember, what is the big U? What is the big U? Okay, the big U is U primed. U prime of 0 is it's a 2. So we're gonna put a 2 here. 0.2 times 2 is a 0.4. And therefore you have K V2, which is 0.2. V equals, okay, in the same way, then the V is going to have like the same things inside. So it's going to be like 0.3, like we saw with the KU1V1. It was the same arguments. So the same arguments giving us a 1.6, a 4.2 coming out of these multiplications, a 4.2, and then you have a 2.0, and then a 5.35, which is 0.2. And then it is 5.35. And then the 5.35, if you use a calculator, we get 1.07. That is KV2. Let us do KV3. KV3. Right, let us do KW2. Okay, let us do KW2. Right, so if we decide to do KW2, let's check it out. KW2 is 0.2, 0.3, 1.6, 4.2, 2.0, 5.35, which is 0.2. So this one is going to become, we're going to use the first equation like we did. So if we move all these things to the other side, then it's going to be like t plus 1, but the t0 is 0.3. So it's going to be 0.3 plus 1. And then it is multiplied by the w squared. And w is t u v w. W is the second last, giving us a 2 squared minus 2 into 1.6, 4.2, 4.2 plus 1.6 cubed, not 0.3. And then you close. So which means with KW2, which is minus 0.6, 377. Okay. So now let us deal, that is KW2. Let us deal with the next one. So now we have K. Let us find right now KX2. KX2, it's going to become 0.2 big X. Okay, the arguments inside are the same. We showed the details with the first KU2, and then the 0.3 is going to actually just recur from there. The 1.6 will occur in the same way. The 4.2 will occur in the same way. The 2.0 will follow suit. And the 5.35 will also follow suit. With this mentioned, is 0.2, which is the x. The x is going to use this bottom one. Right, so it's going to use this bottom equation. Right, using this bottom equation, then would have essentially the next thing, which is this one. If you divide by 2, it's going to be 3u. This is t. U is 1.6. So it's going to be 3u if you divide by the 2. And then move everything the other side, to the right-hand side of the equation. Okay. Okay, so there's going to be a 3u minus 0.5. 0.5. The sign of the sign of naught, because of 0.3, because that's T0. T0 is this one, 0.3. That's why sign of 0.3 in this equation, sign of 0.3, because you're taking the VW prime, you're moving everything across to the other side, divide by 2. So it's going to be minus 1/2 the sign of T U primed V primed plus 3u plus T plus 3/2. Okay, let us deal with this. So now it's going to be a U primed. What is the U primed? U primed is W, and W is the second last. Second last is 2. Next, we have V primed. V primed is X. X is which one? Is actually the very last component, 5.35. Like so. We add also the other things like your twice T, right in the bottom. Okay, would have the twice T divided by 2, got only a T, and the T is 0.3. And then now you're going to add also 1.5. Using a calculator is 1.0038. U at 0. Okay, let us deal with this. What exactly is this? So I want us to remember something. We then said the adaptation of these is consistent with the use of this algorithm here. This one, UVWX. So we're going to use this one, UVWX. So that is what we're going to use. That is what we're going to use. Let's use this one. So now we're going to have this. So we're going to use like U UN plus 1 is, this is the formula we're going to use. UN 2/3 K U1 plus 1/3 KU2. Okay, this is the formula we use. Vn plus 1, Vn plus 2/3 K V1 plus 1/3 V2. Wn plus 1. Wn 2/3 KW1 plus 1/3 KW2. which means xn plus 2/3 kx1. Okay, these are like the formulas we're using. Kx2. But we've already got the rest of these. Like ku1 we've got, ku2 we've got, kv1 we've got, kv2 we've got, kw1 we've got, kw2 we've got, kx1 we've got, kx2 we've got. So the next thing now, the next thing right now becomes the following. It becomes the following. It becomes that when we are dealing with this, we're going to then be able to achieve the following notion. We're going to be able to achieve the fact that we have the following. Yep. We're going to have precise the following. Let us analyze this together. U of 0.2 is going to be U0, but U0 is 1. KU1, 0.4. KU2 is 0.4. V of 0.2 is 3. Plus 2 over 3, which is 0.8. One over 3 is 1.07. Not 0.2, which is 0.2. U primed is W. U primed is W according to what we said. You know, U primed is W, so that U primed of 0.2 is W of 0.2, but W of 0.2, then it's going to be what? According to these, it's going to be like W0, and W0 is the second last component, giving us a 2 plus 2/3 KW1. KW1 is 0 plus 1/3 minus 0.6377. V primed of 0.2. Okay, look. V primed is x. So we're going to have x of 0.2. Right, so what would x of 0.2 be? Right, x of 0.2, according to this, is going to be x0. But this is T, U, V, X is the last component. Right, so X, if you are dealing with X0, right, and so dealing with X0, you'd have exactly the following. Okay, X0 would give us exactly the following. Yeah, so it's going to be exactly 4. Why? Because X is V primed. V primed of 0 is a 4. So that's why it is a 4. Plus 2/3 of kx1. We've already got kx1 before, but we used the calculator and we got 0.9 plus 1/3 of kx2, 1.0038. Okay, which is the following, which is exactly the following, which is 1.4. Using a calculator here, you'd get actually exactly 1.4 in the following manner. Okay, because the calculator is allowed in the exam for this module. Right, if a calculator is allowed, then you can be able to then say, for instance, 1 plus. Okay, I can put in brackets like this and have 2 divided by 3. 0.4 plus 1 divided by 3. 0.4. We get exactly 1.4. So you'd have, for instance, a 3 plus 2/3. 2/3 of 0.8. Close bracket plus open bracket. 1/3. Close bracket, which is 1.07, which is 3.89. Approximately 3.89 is this one here. Right, 3.89. And then we just finish off with this. Right, so we have, for instance, the number 2 plus 2/3. 0 plus 1 divided by 3. 1 divided by 3 minus 0.6. Right, so now we then have 1.79. 1.79. 1.79. So 4 plus 2/3. Okay, and then you close bracket. And then you multiply by 0.9. You add to this close bracket, and then you add to this 1/3. Right, you add to this 1/3. Okay, just showing the calculator work, because you don't use softwares or computer programs to do this in the exam. You need to be able to use your calculator, as we're doing, to be in a position to get the answers. So at this point then, you have a 4.9 to 4.9346. You can write just 4.93. Right, which is 4.93. And this becomes the final answer to this particular problem. So a couple of things then are very important. The final answer is given by these particular formulas to the second order differential equations. But we need to first get our KU1, KU2, KV1, and so on. And so now after that, then we're able to then say we can be able to get, because the question said use the second order Runge-Kutta method with H equals 0.2 and A equals 2/3, B equals 1/3, alpha equals beta equals 3/2 to find U primed, V and V primed at T equals 0.2. So that U at 0, we've got U at 0.2, because we're supposed to find U. So we found U at 0.2, which is 1.4. And then U primed, which is, actually we've seen that U primed is what? It's W. Or we found U primed as it is, which are started with W. And so the V of 0.2 we've got 3.89. The U primed at 0.2 is 1.79. And then the V primed at 0.2 is 4.93. It's 4.93. So this becomes the solution to the problem that pertains what we call the second order Runge-Kutta method. The second order Runge-Kutta method. Right, so we've paid attention to this particular second order Runge-Kutta method, and we have since learned a thing or two from this, and it is therefore very important that we pay particular attention to this, because it is likely to surprise you, but the way it is done in a way that is very, very sneaky. Okay, but yeah, the structure remains like this. But obviously, this discussion is being recorded for control and quality purposes, but you'll always have access to the recording. I want us to look at another notion in view of a couple of things that we need to be able to solve. We've learned a lot about the other methods, like your Adams-Moulton, and so on, your Paddy approximation method. We've learned all that, but I want us to have a discussion about the next method that must be known. For example, the power method has been learned, but yeah, it is the biggest matrix you'll ever get is 3 by 3. It came before the 3 by 3 matrix came before, and we looked at the 3 by 3, and on the way we looked at the 3 by 3 matrices here, the matrix A with its inverse, is how obviously one needs to deal with these kinds of problems. But there's something we call the fourth order Taylor polynomial, fourth order Taylor method. Fourth order Taylor method. Let us deal with the fourth order Taylor method. Right. So now, if then we're dealing with the fourth order Taylor method, what exactly do we anticipate to learn in a case like this? And what should be known? And perhaps what should need to be known? Okay, because we need to make sure that we master every single bit of what must be learned in this particular module. Right, so let us pay attention to what we term the second order, rather the fourth order. And fourth order has to do with the highest derivative, the highest derivative in this. So now, obviously, you need to use the fourth order Taylor method with delta x equals 0.1 to solve the differential equation. So this question here, do not just think it's a question. It is from the October-November. It is from the October-November 2023. This one, first question. So I'm trying to make sure that we familiarize ourselves, because we have access to, I have access to pretty much all the papers. So what we then do, we approximate. Right, so we approximate y at the following. Right, so if you need to, obviously you know that y at 0 is 1. Right, y at 0 is 1. Right. So you're going to have 0.1. So we approximate this one by the truncated Taylor series. By the truncated Taylor series. And the truncated Taylor series would be, for instance, y at 0.1. It's therefore going to be the following. Therefore going to be the following. Now, I want us to write first a general formula so that these can make more sense. So what we then do first is to say we find y at x. Y at x becomes y at a plus y at a plus. Then we're going to write the following and say it is exactly the same as what? Right, so if you write y at a, there is associated with it an x, but it is associated with, so you can write, for instance, y primed at a divided by 1 factorial. And then we're going to add the following. Okay, so we're going to have, for instance, y primed it at a over 1 factorial, then it is x minus a, y double primed at a, x minus that squared over 2 factorial. And then you have the third degree, x minus that cubed over 3 factorial. Okay, fourth order, then you're going to stop at 4. 4 at a, x minus that 4 over 4 factorial. So this would be the truncated Taylor series. Okay, let us practice with this together and try to make sense of these. So now, if we want to actually be in a position, now we know our delta x, it's 0.1. Right, so if we want to find evaluated at 0.1, then we're going to have exactly the following. So we're going to have y at 0.1. Right, y exactly at 0.1. Right, so if you're dealing with y at 0.1, we actually obviously need to reason what happens next. What happens next? And this becomes precisely what happens. But also, I want us to bring to your attention some of the things that are involved. So there's a tendency to therefore call this one here a delta x. Right, a tendency to call this one here a delta x as it is. And here, this one becomes the delta x, and then you square it. Right, so it becomes exactly the delta x, and then you square it. Delta x, etc. Okay, let us reason these together. So you're going to have to say if this is our x is 0.1, and we need to then determine this, at what point would this therefore become very, very important? So there is y at a. So y at a could therefore be determined at what? Right, because you know very well that y at 0 is actually exactly a 1. Right, if y at 0 becomes exactly 1, then you need to consider the fact that if you put these as y at 0, and then you come here, y primed at 0, the x becomes 0.1. So that is with the delta x there. And then y double primed at 0, at 0. And this one is 2 factorial. And then our x is 0.1, but our initial point is 0. So it's 0.1 minus 0, making it 0.1 squared. Okay, you write this one, triple primed at 0 divided by 3 factorial. And then obviously, you can write a trivial step here. You have 0.1 minus 0 cubed. And then you have y fourth power at 0, which is 0.1 minus 0 to the fourth power. Okay. Now, we have the following. Okay. All right. So now you'd have y at 0.1 approximately the same as okay, so let's continue with our analysis of this. But also you would need some derivatives, like our y primed, which is this, is y squared. Let us find some derivatives. Y double primed, we find the derivative of these is 2y y primed. Y triple primed is 2y primed y primed plus 2y y double primed. Y to the fourth power. Y to the fourth power. Which is 2y double primed y. 2y primed y double primed. 2. Okay, we're using the product rule, please, of differentiation. So we want to go up to the fourth order. Okay, so let us proceed together and practice this method. Okay, this method called the fourth order Taylor. So what are we then going to have here, for example? What are we then going to have here? Okay, so okay, yeah, we're still looking at the fourth order derivative. Let us deal with the fourth order derivative. Let us deal with the first order derivative. Okay, yeah, we're still here. Well, yeah, because we're saying we actually approximate this one by the truncated Taylor series. Okay, we want to find the derivative of these, giving us the fourth derivative from the third derivative. Okay, so we differentiate this one because we first found the derivative when we got this one, 2y y prime, and then we got the derivative of the second derivative of this second derivative, and then we have 2y prime plus 2y y double prime, and then you find the fourth derivative, which is 2y double primed y primed, 2y primed y double primed. So we differentiated this y primed and it became double primed. But the product rule plus, we keep this one constant and then differentiated the y primed, we got y double primed. And then we come to this one. And then it is plus 2y primed y double primed plus 2y y triple primed. Okay, let us see what we are getting here. Let us see what we are getting here. So if we agree that this is the first derivative, which is exactly y primed, so it would therefore mean that our y primed is the first derivative, which is the dy dx. Okay, so it becomes dy dx, but this dy dx is y squared. And then we need to get, we have y at 0 is 1, and then what is y primed at 0? Y primed at 0 is y at 0 squared. What is y at 0? Is 1 squared, which is 1. And then we find the next derivative. So if y primed is this, then y double primed from here would therefore become y double primed, which is equal to what? So y double primed, which becomes 2y y primed at 0. Okay, so y double primed at 0 is going to be 2y at 0, y primed at 0. 2. What is y at 0? Y at 0 is 1. Y primed at 0 is also a 1. And this becomes 2. This gives us y double primed at 0, which is a 2. Now we have y double primed, which is 2y y primed, triple primed, triple primed. So it is 2y primed y primed, 2y double primed. Okay, by the product rule, we differentiate first this y, which makes it y primed, keeping the 2 and the y primed constant. And then we have the 2y, we keep constant. The rate of this one becomes y double primed. What is y primed? The y primed is 1. Another 1. Y at 0, it's 1. Y double primed is 2. 4 plus 2, 6. 4 plus 2, 6. 4 plus 2, it's 6, yeah? Let us do one more derivative. So, because we're dealing with the fourth order. Right, so dealing with the fourth order, we're going to do the fourth derivative. Of course, it's a function of x. We come here. Let's find the derivative of this. So the derivative of this one here is going to become 2y double prime. First, we differentiate this one, getting a y double primed, y primed plus 2y primed, y double primed plus 2y primed, y double primed plus 2y triple primed. Correct? Let's check. We first differentiate the y primed, it becomes double primed. This one you keep constant. Plus, you keep this one constant, differentiate the next one. Okay. Then you come to this one, differentiate the first one, getting a primed. Differentiate the last one, getting a triple primed. What is y double primed? Y double primed is a 2. Y primed is a 1. Y primed is 1. Y double primed is 2. Y primed is 1. Y double primed is 2. Y at 0 is 1. Y triple primed is 6. So that y at 0, so this one is the fourth derivative at 0. Right, so it becomes the fourth derivative at 0. Okay, you're just practicing this one from the October-November 2023 paper, because we discussed the one of January and we're done with it. And then now we're dealing with this one. Okay, if we're doing this, a 2 times 2, it's a 4, plus 2 by 2, it's another 4, plus 4, plus 12. So the fourth derivative at 0, and then 4 plus 4 plus 4, 12. 12 plus 12, 24 it appears. Let us check everything right now. So we'll come here and then say, what is y at 0? Y at 0 is a 1. Y primed at 0, we check it. Y primed at 0 is also 1. Y primed at 0, it's a 1. 0.1. Y double primed at 0 is 2. Y double primed at 0, it's 2, which is 0.1 squared. Y triple primed at 0, Y triple primed at 0, it's a 6. It's exactly a 6. Y triple primed at 0, it's a 6. You divide by 3 factorial, which is still 6. And then you have 0.1, you cube it. Y quadruple primed at 0 is a 24. Y quadruple primed is a 24. 0.1 to the fourth power over 4 factorial. Which means y at 0.1 is approximately 1 plus 0.1. 2 divided by 2 is 0.1, which is square. 3 factorial is 6, giving us a 0.1 u cube. 24 divided by 4 factorial. 4 factorial is what? 4 factorial is the same as 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. But all this gives us what? Exactly 24. So that at this point, then 24 over 24 here is a 1. But this produces 0.1 raised to the fourth power. So we want to find an estimate of 0.1, and let us get the answer using the fourth order Taylor method. So we have the following, which is 1 plus 0.1 plus 1 plus 0.1 plus 0.1 squared plus 0.1 cubed plus 0.1 to the fourth power. Okay, which is 1.1. Right, appears that we actually obviously have 1.1111. If that is actually exactly the case, and that is what appears to be the answer to this particular problem. The answer to this particular problem. Right. So now, using the fourth order Taylor method with delta x equals 0.1, we have actually managed to solve this particular problem here. So obviously, I mean, think about these and to make sure you can internalize these. But as indicated, these aren't just ordinary questions, but they're past exam questions. With this one here has been a question that featured in the October-November 2023 paper. October-November last year. So yeah, it's October-November again of the subsequent year this time around. Think about it and make sure you can understand and interpret this. I think that it was awesome having this discussion today. There are tons of other questions that remain, like your this one. As part of the October-November 2023, as part of October-November 2023, there was this question on what we call use the modified Euler method with 2 corrections. 1 correction, so we're going to do 1 correction and then we're going to do 1 recorrection. And the marks were 8. Total marks for, so question 1 had like A and B, and we did A right now on the fourth order Taylor, and then the second method is the modified Euler. So the couple of those methods that feature, but I'm sure that we've done like the most already. But yeah, I'm just mentioning these as part of the question 1, October-November 2023. We've done the rest of the other topics, but yeah, I'm saying watch out for these things we're highlighting from time to time. But however, it was awesome having this discussion today. Right, and I think that obviously we certainly keep in touch, and as we think of our way through to the level of preparation that we most certainly desire. But thanks again for joining us. It was awesome having this discussion. Until next time, I think you need to take care and enjoy yourself the most as you prepare for this exciting module. Your calculator is your everything when it comes to doing approximations. We do a lot of approximations in applied mathematics, and obviously this module is not at all different. Right. From us.
Thank you so much.
Thank you so much. From us, take care and goodbye. The recording is coming in the next few minutes. Okay.
Thank you so much.
Thank
Bye.
you and goodbye. Goodbye.